I'm Xiang. So I'll be talking about graph transformers to multi-electric flow based on the actual paper this year of the same name. This is joint work with Lawrence Kern and Suresra from Duke and TUM. So, quick overview, graph neural networks have been successful for many learning problems from graphs, ranging from social network analysis to chemistry and other scientific applications. And originally they were based on convolutional neural networks, and more recently people have adapted the attention module for graph neural networks. And there are lots of variants of it, at least a few examples on this slide. And they have made certain modifications. For example, you only attend to the neighbors of your graph, each node. Some of them have incorporated, edge information, and generally they use some kind of additional encoding based on graph structure. But for the purpose of this talk, for the most part, you will not be looking at these modified graph transformers. Instead, we'll focus on the ability of the standard, the linear transformer, which is, I guess, simpler than the standard transformer, to implement certain graph learning algorithms. For a number of fundamental graph problems, such as electric flow, effective resistance, Keith kernel, and eigenvector computation. The motivations are twofold. First, we want to understand how the standard linear transformer processes graph value data. And second, we hope that this understanding allows us to design better transformer architectures for processing graphs. So this is what I mean by the linear transformer that we'll be looking at for the most of this talk. The input is some Z, which is a matrix. Think of it stack of tokens, which I'll define later. It's got a bunch of layers. Each layer consists of an attention module, specifically a linear attention module, plus a linear transformation. So it's kind of as if I took a standard transformer, took out the nonlinearity, replace the MLP layer by a linear layer, and then put them in parallel. And so that there are going to be four kinds of parameter matrices: the value, key, and query parameters for attention, and a WR matrix in red, which is the parameters for the linear layer. And next, I need to define some basic graph notation. So given a graph is defined by a set of vertices and a set of edges. So here's an example graph on the slide. It's got 5 vertices, 0 to 5, and it's got a bunch of edges. For example, vertex 1 points to vertex 0, and vertex 1 also points to vertex 2. So the graph problems we study today are going to be defined for undirected graph. However, we're going to assume that each edge in the edge list has an arbitrary orientation, because it's convenient for various reasons. And finally, in general, we consider weighted graphs, where the weights are given by a function r, which maps from each edge to a real number. The choice of the letter r is really because it's related to resistance that we'll look at in the context of solving electric flow. So given these definitions, we define something called the incidence matrix of a graph. And before that, I guess we'll let n denote the number of vertices, and d denote the number of edges. And this is a somewhat deliberate choice of notation because each vertex in the graph is, you'll see it's kind of the analog of a token when you input to the transformer, and each edge is playing the role of a feature. So the edges, the feature. We define the incidence matrix as follows. The incidence matrix is n by d, and the incidence matrix, ijth entry of the incidence matrix is, so ignoring the resistance, the ijth entry of the incidence matrix is -1 or +1 if vertex I is incident to edge j, and -1 +1 depending on which direction the edge points. So bottom left of this slide, I have the incidence matrix for this graph. the first column of the instance matrix corresponds to edge 0. And you'll notice that each column has exactly 1 plus 1 and 1 minus 1 entry because the edge touches 2 vertices. And just for another example, edge 3 corresponds to the third column of this instance matrix, and again, it has a plus 1 and minus 1. On the other hand, each row of this instance matrix can be seen as an encoding of the connectivity of that vertex. So V for vertex 2, that's the third row of the instance matrix, and it tells us that 2 is connected to 4 edges. And finally, the instance matrix is related to something called the graph Laplacian. If I take dv transpose, that gives me a graph Laplacian, which is an n by n matrix. And the graph Laplacian is also equivalent to the identity minus, oh, sorry, it's not identity, it's degree times identity. Minus the adjacency matrix. But in some simple diagonal matrix minus the adjacency. So this is the electric flow problem. Let psi denote a vector of demands. So in other words, I want to route some amount of flow in the problem. And by flow conservation, psi transpose the all ones vector is 0. So flow I don't produce flow out of that. For example, on this graph, if I want to route 1 unit of flow from the 0th vertex, which is the source, to the 4th vertex, which is the sink, psi will look like this. So it's got a 1 and minus 1 corresponding to the source and sink, and zeros everywhere else. The goal of electric flow is to find an energy minimizing flow path. So edge is a flow that assigns a flow value to every edge in the graph. And this is one reason why it's convenient to consider edges with orientation, because that tells us which direction the flow goes in. And so we want this flow to satisfy the demand side. So this constraint basically encodes that your this flow must route the correct amount of things into and out of each edge. Oh, sorry, product. At the same time, we want that there are many flows which will satisfy this constraint, and we want a flow which minimizes the energy given by this objective in green. And intuitively, R represents the resistance of an edge. And so R times F squared is the resistance times current squared, which, as we know from high school physics, is the energy of a electric flow. Very conveniently, there's a dual formulation of this electric flow problem. So, the primal problem is find the electric flow, which is assignment of flow values to edges. And there is a dual problem, which is assigning potentials to vertices. So we want a potential assignment phi, which map from each vertex to the electric potential. And to do some simple reality algebra and get the objective on the bottom. And there is a nice interpretation that the primal problem is current square times resistance. The dual problem is potential loss square divided by resistance. Again, a measure of energy by physics. So we'll primarily be concerned with the dual formulation. And so this is the problem. Given a graph G and a set of k different demands, psi 1 to psi k, where G and psi can differ with each different input, we want to train a transformer which outputs the energy minimizing potential for each of the k demands. So the transformer will output a bunch of vectors. We'll read a subset of them, and for each of those vectors, we want it to be the energy minimizing potential assignments. The setup looks like this. So this is the transformer I described at the start of the talk. It's linear transformer. Each layer is a linear tension in parallel with a linear layer. With a linear layer. So the input to the transformer, very importantly, is a Z matrix where each column can be thought of as a token. And each there are n of them, so one column for each vertex in the graph. And the encoding of the ith column is given by this thing. So it contains three things. First, it contains the corresponding row of the instance matrix, and that is where the transformer gets all the information about graph connectivity. Concatenated to B is this green vector, which is the demand on that vertex for 1 to k. So if I have k demands, this is the vector of n to k. And finally, there is we concatenate at the very end a stack of zeros, and that's kind of like a scratch space that's needed for our construction. In practice, having this stack of zeros at the end is also helpful. So I guess in some sense it's necessary. We'll let the capital Z sub I denote the intermediate output after layer I. And just as we have three different things concatenated in the input, we'll give names to the corresponding three components of BI. So the first k rows, we'll call it BI transpose. The next k rows, we'll call it BI transpose. And the final, I guess, k rows, we'll call it phi. And intuitively, the phi encodes the solution of the transformer for the corresponding demand. So by solution, I mean the electric potential assignment at layer I. So is everyone clear on the setup? So the theorem is as follows. There exists a construction, so specifically a choice of weights for the values, query, key, and the linear layer at each layer, such that for any graph G with incidence matrix P, for any set of k demands, every layer of the transformer implements one step of gradient descent with respect to the electric flow objective. Specifically, if you let psi be as defined on the previous slide, then going from psi ij to psi I plus 1j, it takes one step of gradient descent with respect to f of psi. That's a typo, it's psi j. But,
is it exponential minus L or exponential minus T?
Minus T, I'm sorry. Maybe, yeah, I can take it. Sorry. Fine. Okay. And this should be here. And so after T layers, the distance between the transformers. Okay, after T layers, the difference between the transformers output and the optimal solution contracts as e to the minus t times some delta, which is the step up. And the optimum solution of this electric flow problem is actually pretty simple to write down. Right? It is L to the inverse times your demand. And this result shouldn't be very surprising for those of you who have looked at this in context learning, gradient descent construction. And the similarity goes beyond just the current statement. Even in the construction, it's very similar. Because we look at the objective of electric flow is minimizing a quadratic, right? So L here is kind of playing the role, the analog of your gram matrix in linear complex learning. Phi is playing the role of your theta, and psi is playing the role of x transpose y. So it is a bit different because you're not given x, y pairs, right? You're given x and x transpose y. And it's because of this difference that we needed a bit of extra scratch space. Whereas in the in-context learning linear regression setup, you just needed basically the B matrix and the demand factor. So this specifically is the construction that we have for implementing gradient descent. I guess I want to point out a few things. First, if you look at the WQ transpose WK matrix, it's 0 everywhere except with the identity matrix in the top left block. And recall that our top left block is the B matrix, so B transpose, or B transpose, sorry, I forgot the one of them. So Z transpose WK query P Z exactly recovers the Laplacian. And the value matrix performs this update. The other thing to note is that because the value matrix has 0 on the first row, the first block and second block, and the linear layers matrix also has 0 on the first and second block, the B and side parts are never updated. So you just keep those same features going from layer to layer, and the only thing you update is the solution block. Which again, I think in the linear regression context learning setting for basic gradient descent is very similar. So there, we also showed this faster electric flow solver, where instead of needing log 1 over epsilon layers, we need log 1 over epsilon layers. There was a talk this morning as well talking about log 1 over epsilon for iterative Newton's method. I don't know iterative Newton's method very well, but based on pattern matching, I suspect that there is a connection there. And the key difference between this fast electric flow solver versus the gradient descent based electric flow solver really is that we are we iteratively update the features themselves. So we are no longer just carrying the same feature vector from layer to layer.
So what do you precondition this with? Like this iteratively precondition thing? You preconditioned on each iteration, right?
Yes. So we're transforming, roughly speaking, the B matrix by identity minus delta Laplacian times the B matrix each time. So it's kind of like this gradient plus thing that was done for in context learning gradient descent. The next slide maybe shows that more clearly. Also, another thing, disclaimer is that the setup for the iterative precondition gradient descent is a bit different from the gradient descent setup in terms of how we format the input. You input the Laplacian instead of the instance matrix, but I won't go into that detail. And here's the key intuition behind the proof. On the left, we have this Taylor series expansion up to the power of t terms, and every step of gradient descent basically corresponds to one additional term in this sum. On the right, we have a different kind of expansion. By Taylor expansion, I mean expansion for pseudo inverse of the Laplacian. So this expansion on the left is equivalent to this product-based expansion on the right, and t terms on the right is equivalent to 2 to the power of t terms on the left. So just in terms of the number of terms you have to implement, the right product-based term is much more efficient than the left sub-based. And so this product-based expansion was, I think it's been around for a very long time, but I learned about it in this Spillman-Tong's paper on fast SDD solvers, which was related, which is a more general form of fast electric flow solvers. 2014 paper, I think. And so as I said, each term of the gradient descent transforming implementation implement one extra term of the Laplacian. And each extra layer of the preconditions is basically precondition gradient design implementation implements an extra product term on the right, and which is exactly the reason why you get a log when the reps run complexity. And again, this comes back to iteratively updating the feature. So that's it for electric flow. We also have constructions for effective resistance and heat kernel. So I guess effective resistance and heat kernel are two things which people use for partition encoding in modern graphical network, and that's the motivation why we look at them. And in general, for all these things, the constructions converge at least exponentially fast. So log one route layers needed. And here's some experiments, syntactic experiments. We try two kinds of graphs, fully connected graphs, and something called circular skip link graph, which I guess are kind of green graphs, but it's skip connection. And you know, each time we generate a graph is random pathways. And we train the transformer and check on different sides of time graph. And the loss denotes the error between the transformer's output and the target matrix of true optimum potentials. As you can see, for each of these problems, the transformer is able to learn the algorithm that gets pretty good loss in a small number of layers. Here's another set of experiments studying whether how one does it instead of using a linear transformer, we use a softmax activated transformer, which I guess is the real transformer. And it doesn't do nearly as well. So you can see that the softmax transformer and the two-headed softmax transformer have a significant gap to the linear transformer. And again, given what we know from the linear regression in context learning problem, is not that surprising. I believe that softmax activated transformer also does relatively poorly for that problem. The final experiment I want to mention is that under our construction, the weight matrices are very sparse. So this has a bottom right log, which is identity. This has a top left log, which is identity. And so the idea is that we can impose. So if you really believe this construction is, the thing that the transformer is learning, then we can impose sparsity and scale identity structure. So for the green blocks I showed here, we're just going to enforce that those parts of the parameter matrices are 0. For the blue top left part, we're going to impose that as a scaling of identity, so just a scalar parameterization. And one benefit of doing this is that it significantly reduces the parameter count. So despite the way I wrote this matrix, most of the matrix goes in the top left block. Because the top left block is d by d, d is the number of edges for a fully connected graph is n squared. So d is it can be much bigger than n, which is in turn bigger than or equal to k. Because why is n bigger than or equal to k? Because I guess if it's the number of demands, and once you have solved n demands, you kind of solved everything. Solving n demands on the electric flow problem is as much as you need to invert the entire Laplacian matrix. If you inverted the Laplacian, then you don't need to solve anything. So besides being parameter efficient, turns out that enforcing this sparsity also lets the transformer achieve much higher accuracy. So I'm not sure if it's very feasible, but this is -10, and this is -12, this is -12, and this is -14. So these are, some pretty weak evidence that this kind of constructions do make sense. Finally, I'll talk about this problem of computing eigenvectors. And so again, the story is pretty similar. We show that there exists a choice of these linear transformer parameters such that given any graph G, it computes the bottom or top k eigenvectors of the Laplacian in its forward path. And the main proof idea is that the transformer, the linear transformer that we set up is capable of implementing this subspace iteration algorithm. Certainly, which consists of, repeatedly doing two things, right? Take your estimate of the top k eigenvectors, multiply by the Laplacian, which clearly the attention can do very easily, and then perform this orthogonalization. And so I guess, interesting part of the proof of this is that attention is well suited for orthogonalization, which again is not super surprising, right? Orthogonalization requires you to compute these projections and then subtract them, and the self-similarity matrix is, it's sort of the right thing for computing these pairwise projections. And the final thing to note is that for the construction of this theorem, again, the matrix is a block diagram, which is useful because it reduces the parameters. Here are experiments. The transform is trained to simultaneously recover the bottom 5 eigenvectors. I think this is a 10-dimensional 10-node graph. So altogether, there are 10 eigenvectors. We're trying to recover the bottom 5. On this plot, I showed the recovery error against number of layers for eigenvectors to 5. I omitted eigenvector 1 because all graph Laplacians have the same bottom eigenvector, which is all ones. So that's, you just need to recover constant. And here we see that the bottom eigenvector is recovered first, followed by the other guys. Right.
So the bottom eigenvector is the all one vector?
Sorry, the second to last. So the orange one is this. I never plotted the all one vector goes straight down and squishes everything else.
And for you, how are you getting the from the intermediate layers? How are you getting?
Oh, I'm not getting the intermediate. Each point is a 3-layer transformer trained from scratch, and then a 5-layer transformer trained from scratch. So I'm not. It's not. I trained a 7-layer transformer. Yeah. It is an interesting question. What if I trained a 7-layer and then looked at all the intermediate layers? I made that plot at some point. I don't remember the details, but I think for the first few layers, it's almost not making any progress, and then suddenly it makes progress. But don't take my word for it. I didn't look at it very carefully. So this is, training to recover the bottom 5 eigenvectors, and it starts by recovering the bottom eigenvector. So here's the plot showing where we're trying to recover all 10 eigenvectors. And the interesting thing here is that the top eigenvector gets recovered first, followed by the second top and third largest, and so on. So it's kind of the opposite of the previous one, which I thought is kind of interesting. Maybe the transformer learned to invert the Laplacian first before doing the power subspace iteration. But I don't know exactly why this is happening. And as a concrete application of this theory, we try to use a linear transformer to learn better positional encodings. So in practice, graph neural networks, and by graph neural networks, I mean these complicated, fancy graph neural networks with their, attend only to the neighbors mechanism and lots of different things. They use the Laplacian eigenvectors as position encoding for these nodes, because those eigenvectors tell you how the nodes are connected. And this is makes a significant difference for improving downstream accuracy. So on this diagram on the right, which I took a screenshot of from this paper, Generalization Transformer Network to Graph, this is like a real graph transformer I mentioned at the start of the talk. Lots of fancy things going on. H is kind of the tokens. You can think of it as the tokens at intermediate, some intermediate layer, and the position encoding of the nodes are fed to each layer. And so if you really believe that the linear transformer can compute Laplacian eigenvectors, then if you replace the positional explicit position encoding by the output of a linear transformer, which I described earlier, then we should do as well, if not better, in terms of downstream accuracy, right? So in the worst case, I guess one hopes that the linear transformer learns to recover the eigenvectors and it does the same thing. But maybe it learns something better. So here's the diagram. We take out the explicit pandas and we feed in, replace that by our output of the linear transform. And so the task was to predict the constraint solubility of molecules on two datasets, zinc and QM9 is a very commonly used benchmark. And we consider three kinds of architecture. So the first is the graph transformer without any position encoding, so that should do pretty badly. The second is a graph transformer that uses explicit Laplacian eigenvector as position encoding. So that does much better. And the third thing is to use graph transformer, but instead of Laplacian eigenvector position encoding, we use the output of linear transformer. And so in the last case, I guess we train both the graph transformer and the linear transformer with at the same time. And so one thing to note is that the linear transformer needs very few additional parameters. So the graph transformer has like 100,000 parameters, and the linear transformer has a couple hundred. For the zinc dataset, there is a significant improvement in replacing the hard-coded Laplacian eigenvector by the output of the linear transform, going from 0.2 to 0.13. But for QM9, there's very little difference. So it's basically 0.2. One reason I think this might be the case is that zinc is relatively complicated with about 20-something molecule atoms in the molecule. QM9 is much smaller with like about 9 or 8 atoms per molecule. So maybe there's not much interesting thing to learn there beyond the Laplacian eigenvector. Let's see. Oh, and one last thing I wanted to note was that I look at the output of the linear transformer at convergence of training. And I consider a couple of different transformations, including linear transformation, to see if there's even like it is really outputting the Laplacian eigenvectors exactly. And it's not. So it's learning something pretty, I guess, unfathomable for me at this moment for the zinc dataset. The other thing was that it really helped if I initialize the linear transformer to output Laplacian. If I started with a random initialized linear transformer and random initialized graph transformer and trained, I get like 0.1718 accuracy. But it helps. So it helps to initialize the linear transformer to output graph Laplacian eigenvectors, but at convergence it ended up learning something pretty different. And so I guess I'll end here.
So one of the big critiques about using the Laplacian eigenvectors as a positional encoding is that they are non-immune, right? You have to do a trace of cases, right? So I'm just wondering, how does your approach address this problem?
That's a good question. So when I train the linear transformer at initialization to output the Laplacian eigenvector, the loss is up to sign flips.
Okay.
So you will output something. You will output one of those directions. But at the same time, I guess it's also equivariant with respect to the input, at least for the construction, right? In other words, if I initialize my guess for the eigenvectors and actually the signs, the output signs will also be flipped. So I know that for the graph transform plus Laplacian PE, it improved the accuracy a lot if they have this random sign flip before inputting the Laplacian eigenvector. For us, we didn't see a benefit for random sign flip. So we didn't do random sign flip, but I can't explain why.
Okay.
Is it possible to show the same convergence rate for linear regression task?
Same convergence rate, log 1 result. I am 80% hopeful that it's not a difficult translation. Because this product-based expansion fundamentally is for inverting a matrix. And so linear regression, you also want to invert a matrix. Maybe you need a bit of extra scratch space in the naive construction, but at least up to doubling of your dimension, input dimension, I think you should be able to do the same thing.
Very nice. We thank the speakers of this session again. So we are wrapping up for